all, guess I should start there. Sorry, obviously I'm doing this from my house, so a little bit of a different tech setup. So yeah, howdy everyone. You're all doing well. Um, and today I will be continuing along with my lecture on planetary surfaces, mainly, really, I should probably entitle it planetary geology, if anything else, but planetary surfaces is what it is. Let's see. Where was I going to go with that? Oh, yes. So for those of you who might be wondering if I'm ever going to get around to actually answering the question, has JWST debunked the Big Bang Theory? Yes, I am going to actually go live with that tomorrow at whatever time it was that's specified. Work has just been getting away from me, so I have decided that I need to focus on the work rather than the play. So that is, I do plan on doing that. And I also do plan on opening it up to guests. I know SC Montreal wants to have a word about it. So if the time is convenient for him, then I may have special guests on for that particular stream. But anyway, what are we going to talk about today? We're going to talk about planetary geology. Last time we left off, I talked about the really cheery subject of planetary impacts and the damage that these impacts can do, the remnants, the cratering remnants that can be left over, and just how frequent I may be having some internet issues. Odd um, because I'm doesn't go terribly awry. Please let me know on your side what things are going awry. Probably Chris telling me my internet is unstable. So I don't exactly know what that means. I think I need to call Cox and find out what's going on with that lately. So what do we so let's continue on. If it continues to be bad, then I may have to reschedule this lecture so till when I get into the office next. Yes, it's awry. Oh, all right. Is it watchable? As this is one of my lectures, I don't want to. I don't want to bear through it if it's not going to be of watchable quality. Well, my unstable connection little thingy went away. So, all right. Well, we'll go on and see what happens. Hopefully, it doesn't reoccur. All right. So, aside from cratering, there are three other mechanisms that I'm going to be talking about which affect the surface of a terrestrial world or a solid world. The next one is volcanism. And volcanism, as you might expect, is the process of volcanic action. It is a process via which liquid hot rock or magma gets pressurized underneath the lithosphere. That pressure becomes high enough that it will actually punch through the lithosphere and then will upwell onto the surface of the world. What this generally does is two things. The first thing that it definitively does is it wipes out the record of any other geologic activity or the history of geologic activity up until that point. That molten rock or that magma acts as a new coat of asphalt that just spreads away from the point where it is punched through the lithosphere. That action is actually one of the reasons why we know that Venus has as I may have mentioned before, one of the more open questions about Venus is that Venus, the Venusian surface, the entirety of the crust is very, very young. Where on the Earth, we can see elements of the crust that are maybe a few hundred years old or even less, all the way out to we have pieces of the crust that are billions of years old. The age of the Earth's crust, from my understanding, is quite varied. You can find very, very young pieces. You can find very, very old pieces. With the Venusian surface, all of it is roughly speaking around 100,000 years or younger, because of a massive volcanic event that resurfaced the entire planet. Again, it's an open question as to why that happened or even how that happened, and whether or not it's going to happen again or has ever happened in the previous eras. But that is our leading theory as to what it is. The other thing that volcanism can do is it actually build up the surface, depending on the viscosity of the lava in question. So we have three different features based on what that viscosity is. Basically, how runny is it? Is it like water or is it more like motor oil? Now, if it's more like water, what you're going to get mare. You're going to get lava plains. And so what we believe with the moon specifically is that very early on, in a period which we refer to as the very early on, as we in a very early on in the history of the solar system, particularly when the basically the end period of planetary formation. Most of the planets at this point are in their stages of cooling. They're still a bit molten, but they're actually getting a little bit more solid. This is when we enter into something known as the era of heavy bombardment. At this point, we have just the solar system is littered with millions upon millions of asteroids or solid bits of debris, and these are going to find and smack into anything larger than themselves. And so the planets, even the gas giants, the moons and the outer moons, were just hammered with asteroids and comets over and over again, and a lot of these were very high or very large impactors. For the moon, we know that there were a few of these that actually smacked into the surface with sufficient enough force that it broke the lithosphere apart, and a massive amount of lava managed to upwell from those cracks, from those impact points, and then cover areas of the lunar surface that are hundreds or even kilometers in extent. And that dark stain that we now see, those are the basalt rock that was the lava that has now frozen and essentially, like I said, resurfaced the lunar surface. That is what we see, those gray stains that I've alluded to before, those the mare that we can see as a naked eye. Those are ancient lava plains. That is lava that broke free very early on in the lunar history, and then eradicated all of the evidence. Oh, my coffee. Excuse me. Eradicated all the evidence prior to that. Now, what happens if the lava is a little thicker? Well, in this case, what happens is that as the lava is upwelling, it will then start to seep into the cracks kind of around the it will upwell, and it will actually start, because of the sort of frictional force, or because it's more viscous, it's more sticky, so it's going to carry that rock along with it and far easier than the watery lava would. And so the rock will begin to upwell. When it does so, there are cracks that are going to form in that, which the lava is then going to flow into. And what ultimately you form is what we refer to as a shield volcano, something that is very, very wide in comparison to its height. Now, depending on where you are, that does not mean the shield volcanoes are not high at all. In fact, some shield volcanoes can be exceedingly large, particularly Olympus Mons on Mars, which, if you plunk it down onto the continental United States, it's basically the size of Arizona. And it is tens of kilometers in height. It dwarfs Mount Everest here on Earth. That is an excellent question, Chris. I would say yes, but I could not give you a definitive answer as to how much warmer the center of the moon is than the crust. I don't think it's a lot. At this point, believe the major heating, the major phenomenon that is causing the heating of the moon is radioactive decay. At this point, the moon is small enough that I believe that most of its energy that it acquired through the accretion process and through gravitational collapse has been bled off into the universe or into the solar system. But I do believe that there is still something of a temperature gradient. I don't think the moon is completely one temperature all the way through. Then the last kind of volcano, known as stratovolcanoes or Mount Doom volcanoes, as I like to think, are these. Well, they look like Mountain Doom. They're cone volcanoes. They're they're much taller than they are wide, at least in comparison to shield volcanoes. And this is where the lava is most viscous. And we see that quite often here on Earth. We see them on Venus. We see some evidence of them on Mars or on the Moon, Mercury, Mars to a certain extent. That's all right, Bellywood. You're always welcome, no matter when you show up. So if it's same thing, if the lava is even more viscous, it's going to stick to the material it's upwelling through even more, causing that material to upwell even further, causing even more cracks. The lava is going to flow into those, and it's just going to cause this cone volcano or stratovolcano, which is sort of the canonical kind of volcano of fiction that explodes and spews lava everywhere. It is from volcanoes that we can thank for not only the formation of our secondary atmosphere, but also for the replenishment of our secondary atmosphere. Later on, I'm going to be talking about going into the specifics of how it is that a planet loses an atmosphere. And this is a process that is ongoing. The atmosphere that we have now, if outgassing were no longer a thing, if somehow somebody shut off the spigot and turned off or hit the breakers and turned off the geologic activity of Earth, there was no more volcanoes whatsoever, then our atmosphere would slowly dissipate into something pretty much akin to Mars over a fairly short geologic or astronomical timescale. I would hazard a guess as to maybe hundreds of millions, maybe a billion years. But the atmosphere would definitively leak off. Because, surprise, surprise, there is no firmament or dome holding in that gas. Thermal pressure, thermal action will actually cause that gas to reach a speed which will escape the gravitational influence of the Earth and bleed off into space. But because volcanism is still a thing, that little bit, that slow leakage that we have is constantly being replenished through volcanic action and through subduction of plates one underneath the other. And this is how we got these such wonderful elements like oxygen, nitrogen and oxygen in the atmosphere. Is that when the atmosphere primarily formed, it was primarily, at least initially, it was hydrogen and helium. Those went away. Those got replaced with nitrogen and carbon dioxide, and then later with oxygen. So what about tectonics? Howdy, real Cygnus. Tectonics is the general term talking about the or basically the compression, or I keep doing that, compression or expansion of the surface due to underlying pressures. In the extreme case, you can have what we have here on Earth, where that underlying pressure has actually caused the lithosphere to crack into separate plates, and those plates can move relative to one another. That underlying action is the convection which goes on in the mantle. I talked about before, there are three ways that a planet can lose heat or transfer heat from the core, where it is the hottest, out to space, where eventually it leaks out. The first is conduction. Conduction is just solid to solid contact, and heat transfer through the vibration of molecules or atoms in one solid right next to another solid or within a solid. Then, at some point, the physical surroundings are going to get to the point that conduction just isn't efficient enough to get rid of the energy. If conduction continued, then what would happen? You would have a buildup of energy, and nature really doesn't quite like that sort of thing. And so it's going to try to find another energy mechanism or energy transport. And in this case, what it does is convection. And convection, just to remind you, is boiling action. It is when a hot packet of, in this case, molten lava, really forms or coalesces near the core. Because it is hotter than the surrounding areas, it's going to float, or literally float. It's going to move upward through the mantle material. It's going to get close to the lithosphere. It's then going to, as it's doing all of this, it's depleting energy into its surrounding, getting cooler, until it's going to essentially reach the same sort of temperature as its surroundings, and then it's going to fall back down, gain energy, and that process is going to be cyclic. Now, the cartoon that we see here is very simplistic. Obviously, we have three convective cells or three circuits. The one on the left goes clockwise, the one on the right goes counterclockwise, and then clockwise again. Again, this is a simplistic look at it. Really, like I said, it's a cartoon just for illustrative purposes. When you have two convective cells, which at the top, where it meets the lithosphere, right underneath the lithosphere, if they're coming together, what that's going to do is, because again, you have viscosity, there is a certain amount of friction between the molten lava and the more solid lithosphere, is that lava is going to bring that lithosphere with it as it moves. So as the convective cells move towards each other at the top, it's going to cause the crust of the lithosphere to compress. And so that is where you get certain mountain features. The one on the left is for us Americans. That is how the Appalachian Mountains formed in the eastern United States. Unlike with the Rocky Mountains that are near the Pacific Plate, the Appalachian Mountains are pretty dead center in the middle of the North American plate. And so the reason why we have mountains there is not actually subduction, which I'll get into in a moment, but actually just good old normal tectonics where it's compressing. And we can see this sort of thing on pretty much all of the other worlds, specifically on the moon, on Mercury. There are a couple of examples that come off the top of my head on Mars as well. Speaking of Mars, what we do find is quite the opposite effect. Is when you have the convective cells moving away from each other on the right under the lithosphere, that's going to cause the lithosphere to stretch, very much like silly putty. So instead of breaking it, it's going to slowly stretch this material out, and it's going to cause striations. It's going to cause it to crack into sort of linear or near linear features or valleys, and cause this kind of striated effect on the surface. If this action is violent enough, then you can have such an extreme event such as the Valles Marineris. The Valles Marineris is a canyon feature on the surface of Mars, which is the deepest, largest canyon in the solar system. I always kind of find it funny that Mars being kind of the puniest of the terrestrial worlds, not quite as small as the moon and Mercury, but it's, obviously not the size of the Earth. It actually has two of the largest geologic features anywhere in the solar system. It has the largest mountain or volcano in Olympus Mons, and is the largest crater system, Valles Marineris, on it. If you plunk down the Valles Marineris, it would actually extend from the eastern to western seaboards of the continental United States. It's immense, and it's also many kilometers deep. I think 4 kilometers deep at its depth. So it literally dwarfs the Grand Canyon. Our Grand Canyon is nothing in comparison to the Valles Marineris. And I'll explain why we believe that Valles Marineris is not the same kind of feature as the Grand Canyon in a moment. And so I mentioned before, we have plate tectonics here on Earth, where we have divided or convective action has divided the lithosphere into a number of plates. I can't remember exactly how many. I think around 8 or so. You have got the Pacific plate, the North Atlantic plate, the Asian plate, so forth and so on. And here you can see, or at least to a certain extent, those arrows indicate the general direction those are going. One of the two pieces of evidence that we have that plate tectonics is a thing is when we look at South America and Africa. It is the best example of where you take South America and it almost looks as if you can fit it inside Africa. So if you take the point of South America, I have no idea if you can see my cursor, but if you take that point and put it into the sort of this underneath area of Western Africa, it sort of looks like it fits. And on top of that, like a puzzle piece. And so on top of that, not only that, but we also see species of plants and animals that are very, very closely related in South America and Africa. The best explanation for why that could possibly be is that these two land masses were at once very close together, or were in fact connected to each other, such that these species could migrate from one to the other. And then slowly over geologic time, these land masses were pulled apart via convective action or tectonic action. And so we really have three mechanisms or three scenarios of what could happen with these plates. You can either have the two plates slamming together, you can have the two plates moving apart, or you can have the two plates moving basically sliding by one another. That is what's happening with the Pacific plate and the North American plate. Those two plates are moving basically side by side or relative to each other. Now, on average, it's a few centimeters a year, but that is an average. And what I mean by that is that it's not constantly moving a couple centimeters per year. It's not a smooth motion. Again, friction is a thing, and these two plates are jutted right up against each other, so there's quite a bit of friction between the two of them. And if there is friction, then there's something opposing the motion. The Pacific plate really wants to be going northwest with respect to the North American plate, but friction is telling it can't. It's getting really hot and bothered. It's building up a lot of pressure, and occasionally that pressure will overcome that friction, and boom, that is where you get earthquakes. Is when one plate slips with respect to the other. Howdy, Nimrod. Yes, big energy storage, and it's variable. So sometimes that energy storage, it only builds up for a very small amount and then releases, and you get very small earthquakes, or it can build up for quite a long time and you can get catastrophic earthquakes, 7, 8, or possibly even 9 on the Richter scale, God forbid. Eventually, though, What's going to happen is that the uh, Los Angeles basin will eventually get rammed up into the chin of Alaska. But again, that will probably, we will probably have to worry about the oceans boiling off at that point rather than the new real estate that's being developed. Or you can have, so now let's look at what happens at when two plates slam into each other. The best examples of that are this plate on the west coast of South America and then the South American plate. They are slamming into each other directly. And what happens there is something's got to give. Ultimately, one of those two plates has to lose. And when that happens, one of them subducts underneath the other one. And so one of the plates basically folds under the other one. That causes the plate that wins, I guess, to bulge upward or kind of crinkle upward, creating very, very tall, very, very long mountain ranges like the Andes. The Andes occur because of the fact that one plate is being subducted under the other one. As the subducted plate goes under, eventually it's going to warm up, and that solid crust or that solid lithosphere is going to become molten again and then mix back in with the mantle material. Such that when two plates are moving away from each other, very much like the South American plate and the African plate are moving away from each other, what you have now is the formation of trenches, undersurface trenches, where the ground has basically literally split apart, and you have upwelling of mantle material. Basically, these hot smokers and these geysers, the Marianas Trench. All of these are tectonic features or plate tectonic features on the surface or on the floor of the Atlantic Ocean. And so here you have active crust being built. You have crust that is being newly generated as form of upwelling lava that gets cooled off as soon as it hits the ocean water, and then that gets carried out and expanded. So in this way, the Earth's surface is constantly undergoing recycling. That some of the older crust is being destroyed, where new crust is being generated. Another classic example of subduction is the Indian subcontinent is slamming into Asia, and that is why we have the formation of the Himalayas. All right, now we have erosion. Erosion is kind of like gravity in a way, in that it doesn't build anything. So impact cratering, volcanism, tectonics has the ability to both build up a structure and tear down a structure. Erosion only tears things down. If you only have erosion acting on a surface, ultimately, in a very thermodynamic sort of way, it's going to grind itself down to basically a smooth surface, very much like with sandpaper on a piece of wood. You keep at it, you're going to get it really, really smooth. Now, erosion, it can come in a few different forms. Most of them have to do with water in one form or another. Rain or glaciers or rivers, but the other one is wind. So we come to the Grand Canyon. The Grand Canyon, unlike the Valles Marineris, is an erosion feature, meaning that over millions of years, the Colorado River has, as it moves from, I guess it's northeast to southwest, as it moves toward the southwest, it is acting like sandpaper. The water goes across the surface, and it takes a little bit of that surface with it, carries it downstream, deposits it on, and just kind of deposits it. The material kind of falls down, and then that sort of action happens all along the river. So bits of it are being picked up, transported a little bit, dropped down. Those bits are being picked up, transported a little bit down, and so forth. And so the water is literally cutting out part of that surface over time. And this is something that, again, this is happening ongoing. The Colorado River is constantly flowing. And so while the erosionary effect is very, very slight, on short time scales, give it a million years and you get canyon features like this, which are beautiful. If you've never seen the Grand Canyon, if you've never been to the Grand Canyon, highly recommended. Some specs on it. It's 800 meters deep, or 0.8 kilometers deep. It's, depending on where you are, it can be anywhere from 6 to 29 kilometers wide. It's about 450 kilometers long, and it's taken about 5 to 6 million years to have formed. Oh, I should probably look at that. I'll look into that. Is the Colorado River drying up? It was, but then we had what do they call them? Superstorms. But there was a nifty term for them that I'd not heard before. Something like atmospheric rivers. Essentially, what happened was this winter was very, very brutal to California and Arizona, or northern Arizona, in terms of snowfall and rainfall. So we got a massive dump of water, and the Colorado River has been, a lot of our basin, Lake Mead, has been filled back up. A lot of the reservoirs have been filled back up. So I think the Colorado River is doing just fine, or at least fine-ish, in terms of, overall climate change. So no, I try to avoid talking to or about Ken Hovind whenever I can. Although I will say that I would love to have just one, but I would love to have a single conversation with Ken Hovind and a separate conversation with Mr. Powell, if only to express to them how damaging I believe the two of those gentlemen are in what they're trying to do, what they're trying to accomplish. Smoother brain. So, no, it doesn't reach the ocean. That occurred to me. I was trying to, where does the Colorado River? I don't think I know where the Colorado River actually ends, but I'll get into that in a sec. Also, so now, you can have erosion, obviously, by rain. You can have, basically, rain comes down, smacks into rocks, turns that rock into mud, and then causes that mud to slide down to a lower level. And it can essentially whittle down big things to small things. Then you can have river action, like I said, with the Colorado River and the Grand Canyon, or you can have erosion via ice. The Yosemite Valley is a great example of glacial movement. In that, in the winter, you have in certain winters you have a massive glacier formation, and then as the temperature gets warmer, that glacier will melt and that ice will recede. And as it does so, it quite literally drags that dirt along with it as it recedes, carving out valleys like Yosemite. Excuse me. Then you have erosion by wind, which is most commonly seen in terms of sand dunes. And these are lovely examples where you have sort of the windward side, which is kind of like a dome shape, and then you have the leeward side where it just kind of drops off, where you have this kind of scarp or cliff face in the sand. One of the better examples or contrasts of erosion features is that I've seen recently is looking at the surface of Mars, the surface of Venus, in comparison to either the surface of Mars or, more specifically, the surface of Titan, the moon of the biggest moon of Saturn. Venus has a massive atmosphere, as we know, and as I'll go over in depth. Just a tremendously massive atmosphere of carbon dioxide. And the surface, the top of the cloud deck, the winds can be horrific. They can be hundreds of kilometers per hour. So you have very, very strong winds at the surface, or at the top. But at the surface, the winds only gust to maybe 4 to 5 kilometers per hour. There's basically no wind on the surface of Venus. if you can manage to survive and get down there, it's stagnant. The air is very thick, it's very hot, it's just miserable, and there's no wind. And so the few actual photographs of the Venusian surface we have show that the rocks are very, very sharp. They have very sharp edges. They're not rounded off at all, really, at any appreciable amount, because there's no erosion that happens there. There's no wind, and there certainly isn't any moisture, so you don't have any erosion via rain or rivers, and certainly not by ice. But if you look at Titan, on the other hand, Titan has an atmosphere, has a surface atmospheric pressure very, very similar to us, to the Earth, here on Earth, and its atmosphere is also mainly composed of nitrogen. So I like to call Titan the bizarro Earth, in that it's kind of like the Earth and kind of really not. But in this context, what I'm saying is that on Titan, you do have significant surface winds, you have rain, and you can have erosion via water. In this case, the water is actually liquid hydrocarbons, but I'll get more into that later on. But what I'm saying is that if you look at pictures of the Titan surface, the rocks look very well rounded. They are very significantly eroded, as opposed to the rocks on Venus. And then we come to erosional debris, basically river deltas. So as I was talking about with the river action, the river will pick up pick up material from the riverbed, drag it downstream. Once that material gets dumped into a larger body of water, either a lake or a gulf or an ocean, you can have river deltas set up like this one, where you have these silt features. Basically, that material is now renamed silt, and it just kind of forms these weird muddy plains that come off. This is important because we see the same sort of action on Mars. We can find these river delta type features on Mars, which indicates to us that at one point, liquid water did flow on its surface. Not anymore, but at some point in its geologic history, there was in fact erosion happening on Mars via this water features. And we can also see other erosionary features on Mars due to wind, what we interpret as mudslides, and also the rocks there are also somewhat eroded. We see that some of the rocks that the rovers have come across are actually rather worn down. The edges have been sheared off. Now, there is some wind erosion on Mars actively going, but really, the Martian atmosphere is very, very tenuous, and so the surface pressure is far less than it is here on Earth, and so it would take a significantly longer amount of time for the dust, which is on the Martian surface, to actually sandpaper these rocks down. If you've seen The Martian is a fantastic movie. The only thing they got seriously wrong is the inciting event. That big wind gust that would blown Matt Damon away and prevented him from getting onto the ship, spoiler alert, that would never happen on Mars. The Martian atmosphere is not nearly thick enough in order to propel a human being back that forcefully. So, how do impact craters reveal a surface's geologic age? Now, I had a really snazzy application, but I can't seem to find it, so I'll just kind of describe what's going on here. What's going on is, when we look at this feature, this is a simulation of what a section of the lunar feature or the lunar surface might be, or the Martian surface, or the Mercurian surface, something of that nature. Something where you have a significant amount of cratering that have not been destroyed via erosion action. As I said, with the era of heavy bombardment, you had a lot of minor bodies. You had a lot of comets, you had a lot of asteroids. They were all moving at very, very high rates of speed. And so you tended to have very large impactors at the very beginning, or at least these very large impactors destroyed any evidence of any kind of smaller activity that happened before it. And so when you're looking at this surface, if you look at the surface that is inside those rings, inside those very, very large craters, and there's nothing else on top of it, it's just basically smooth, then we can make the assumption that that is a very, very old part, or one of the oldest parts of that overall surface. But as time progresses, as we discussed before, the chances of future impacts increases. And so we get these additional impacts that land on top of these original larger craters. And so you get craters superimposed on those larger ones, and then smaller ones come and they get superimposed onto those, and so forth and so on. And so when you look at this surface, I can, from a ratio aspect, there's a little bit, this technique is a little bit more sophisticated so that you can actually get a numerical ratio, or if you have some understanding of some other evidence to illustrate the age of when the oldest surface is, you can actually get absolute numbers, but you can definitely get relative numbers by looking at the small circles that are overlaid on top of all of them. That represents the surface that is the youngest. Or when I say the youngest, what I mean is the surface that has been disturbed the most recently, or it has changed the most recently. And then you can kind of count down onto the craters that are being superimposed upon, and as opposed to being superimposed onto. So, for example, I don't know if you can see my cursor, but hopefully you can see that there are certain craters that are sort of mid-size. They are overlapped onto the larger craters, but those are then also overlapped with smaller craters on top of them. So in a very, very rough sense, the small crater on top would be the youngest, the intermediate sized crater would be the intermediate age, and then the large crater would be the oldest. And so in this way, we can get at least a basic understanding of just kind of the geologic age, how this surface aged over time. And again, if we have some way of dating these surfaces in some way, such as, I don't know, going there, picking up a rock, bringing it back, and figuring out how much radioactive material is still left in it, if we could do something like that, who knows when we might actually do that. If we can do that, then we can have an absolute benchmark, and then we can turn these relative values into absolute values. So we can know that, the moon formed roughly 4 billion years ago. The thing with the moon is, a couple of lectures back, I talked about how the core of the moon is different than the cores of any of the other worlds, in the sense that if you take the geometric center and you took the center of mass of the moon, those would not overlap. Those would not overlie on top of one another. So the center of mass of the moon is not the geometric center of the world. And again, this is all to first order. Obviously, none of these worlds are perfect spheres, but in general, the surface or the center of mass is located at the geometric center of the body. For the moon, it's significantly off. And the reason for that, or the reason we believe for that, is gravity. As the moon was coalescing and forming, as it did so, not only was the material differentiating, not only was the iron and nickel falling into the center of the body, but it was also falling towards a center that was closer to the Earth than it was to the overall distribution of the moon. So that is why we believe the moon, the core of the moon is a little bit offset, so that it is closer to the Earth than it is away from it. So we have two sides. which we now refer to as the near side and the far side because of that synchronous rotation. Because of the tidal locking, because of the gravitational effect between the two worlds, the moon is always presenting the same face or the same surface to us at all times. Again, to first order, it does wobble a bit, but for the most part, you basically see the same face. And that face is mostly, or to a large extent, these mare that we see. So this is if you imagine the moon is flat. It is not. But if you imagine the moon is flat, this would be the map of it. And you have that, again, you have these large dark stains that are kind of centered. That is the near side. And so on the edges is where you get to the far side of the moon, which you can see better over here. So now on this picture, we're actually taken from one of the Apollos. You're actually seeing a part of the backside of the moon. And you can see that the backside of the moon is almost completely devoid of mare. I think it has one, which is Mare Orientale, and even that is really on the side of the moon as opposed to the backside. The backside looks almost indistinguishable from Mercury. It's just simply cratering. Now, again, we can use that cratering idea to figure out age, or at least relative age. So this is how we know that the mare actually formed after the moon was solid. It's because we can see here on the sides, Mare Orientale is this little thing, or a little pockmark right there. We can see over here on the left and on the right, we have the lunar highlands. They are heavily cratered. You have craters on top of craters on top of craters. But these mare, if you zoomed in on it, you could see that there are very, very few craters all along that surface. And so that also tells us that the era of heavy bombardment that I spoke of was not ongoing and slowly depreciating sort of event. It was a all or nothing and then a cutoff. So these large impactors occur, broke open the moon. This lava flowed all over the surface. And then there are very actually few craters seen on top of that. And so we believe that these mare formed relatively near the end of that era of heavy bombardment, after which most of the larger impactors had either shot off into the outer solar system or slammed into something. So you can see that, so what I'm getting at is that the mare are younger. The surface of the moon, that is these dark stains, are younger, roughly 3.5 billion years old, as opposed to the lunar highlands that are more like 4.25 billion years old. Here's a better picture of the near side of the moon on the left and the far side on the right. Again, you can see that there is very few of these little lava plains on the far side. And the reason for that is not because of, and actually you would naively expect the opposite. You would expect the far side to have more cratering or more heavy cratering because the fact that, it's on the outside. Well, there's two things to say about that. One is that in the very early times of the moon's creation, the moon was not synchronously rotating. It actually was spinning all the way around. Or spinning faster than it was orbiting, rather. And it just settled into this orientation. So, but we know that because space is so vast, the faces of the moon really, the near side is going to get hit just pretty much just as often as the far side. I mean, the far side is going to get hit a little bit larger, but from a statistical standpoint, it's not very significant. So the question is, so this is again a piece of evidence that shows to us that the core is actually offset towards the near side, because it demonstrates that the lithosphere on the near side is actually thinner, such that these impacts, when they occur, were powerful enough to break through that thinner lithosphere, whereas on the far side, they were not. Hence the difference of appearance between the two sides of the moon. Now, why do the terrestrial planets have different geologic histories? I've already alluded to one in the last, or I guess 2 lectures ago, and that would, of course, be size. But let's go through all three. Well, let's start off with the first one, or with planetary size. As I mentioned in a previous lecture, the total heat content of a world is proportional to the volume of that world, whereas the heat loss is proportional to the surface area of that world. You do some quick and dirty math, and you find that the time scale of heat loss is proportional to 1 over the radius, just simply 1, or actually 3 over the radius. So larger worlds cool off slower than smaller worlds. And this has a large effect on terms of how geologically how long of a time it's going to stay geologically active. So the three things that we know that we believe have an appreciable cause to the amount of heat kept in a planet or generated by a planet is, as I said, the accretion process, the energy of this thing coming together, slamming together, converting gravitational energy into kinetic energy. And then once that happens, you have energy generation through differentiation, where you have denser pockets that are moving through lighter pockets or less dense pockets. That's going to cause a shearing or a frictional heat, and that's going to heat up the world. And then also you have radioactive decay. So accretion happens very, very beginning, and basically you no longer have that energy input after that. Differentiation is also still happening, but it's happening at an ever slowing rate. The Earth is still shrinking a minor amount every year, but eventually it's going to get to an equilibrium point where the tensile strength of the world is larger than the gravitational force or gravitational effect, that is pressure that is trying to bring it inward. But that's still kind of at play. But really the major mechanism right now is radioactive decay. That is what's supplying the additional heat. But it's fighting a losing battle. It is still losing more energy than it is generating. The world is cooling off, but it's only doing so very slowly, or at least slower than a world comparison to, say, Mars. It's still very warm inside the core of the Earth, and so you still have mechanisms like volcanism and tectonics acting in these worlds. So we believe this to be true for Earth and Venus, not so much Mars, definitely not Mercury, definitely not the Moon. You also have the role of the distance from the sun, and this has to do with, these last two are going to have to do with erosion. How much erosion are you going to experience, or these worlds going to experience? Because distance of the sun is roughly going to indicate how much water you're going to have as a thing on your surface. If you're too close, like Venus, it's too warm, and so you're never really going to have. And Venus probably never did have liquid water or ice on its surface at any point. It may have had water vapor at some point, but that too has been destroyed over time. So there's no water, and then to exacerbate things, it's outgassing, replace the hydrogen helium envelope with a carbon dioxide rich atmosphere, which then increased the greenhouse effect, which in turn got rid of any lasting water or potential possibility of ice ever existing on that world. So it's completely barren, a very arid world. Or you can go to the other extreme with Mars. Now, Mars is, at this point, is definitively too cold for liquid water. There are portions on the equatorial region because of orbital dynamics. It gets close enough that you could actually have liquid water in a liquid state for a very, very short period of time, even given the low surface pressure. But we're talking maybe a day or on the order of a day or so. Really no time whatsoever. For the vast majority of the time, in the vast majority of the planet, liquid water cannot exist. It would simply sublimate. It would actually not evaporate. It would sublimate off. The surface pressure is not high enough to keep water in a liquid state. And so given the temperature and given the pressure, any water that is on the planet is going to be frozen, and it's also going to be subsurface, as I've mentioned before. The ice caps that we see are not water, is not liquid or is not frozen water. Well, take that back. You have the northern cap and you have the southern cap. The northern cap is more developed, is larger than the southern cap. The southern cap is almost exclusively carbon dioxide. It's almost exclusively dry ice. Whereas the northern cap has, we believe, a core of water ice, which is then covered in a larger cap of dry ice. So that core of water ice is insulated by the dry ice. And due to the seasonal effects, these core or these poles, these ice caps shrink and grow very, very dramatically over the course of a Martian year. And so in that case, you can have a little bit of erosion action happening at the poles, of current erosion action happening at the poles. But most of the erosion that we see on Mars, aside from that small amount of wind that I was talking about before, most of that probably happened early in its history, maybe 1 billion years ago or earlier, when liquid water did in fact exist on it. And not only that, Mars may in fact have, well, Mars, if liquid water existed, then that also implies that the atmosphere was thick enough to provide a surface pressure such that with the temperature, with the higher temperatures due to the greenhouse effect and due to the higher pressure due to the envelope of atmosphere, you could have liquid water flowing across the surface, creating river deltas, slight canyon features, that sort of thing. And then lastly, you have rotation. Now, with rotation, what that has to do with is weather. Now, if you have something that is slowly rotating, what that means is, particularly at the surface, is you're going to have very slow winds. You're going to have very, well, let me back right off that. When you have slow rotation, that's going to lead to a far less complicated weather system, far less complicated atmosphere, which I'll get into next time when I talk about Hadley cells. But if you have a very slowly rotating planet, the atmosphere really does, for the most part, rotate as a solid body. In addition to that, if you have a slowly rotating planet, then the temperature differentials between the sunward side and the non-sunward side is actually pretty significant. And so you have a sort of a consistency of wind as it moves across. And for Venus, because of the substantial atmosphere, like I said, most of that wind is actually trapped in the upper atmosphere, in the upper cloud decks of Venus. When you get down to the surface, because of its slow rotation, the wind is really non-existent. It's there, we suspect, but really, like I said, it's not significant really at all. It has plenty of atmosphere to move. It just doesn't have any kind of force to move it. I should really back that up. I mentioned before that the temperature differential between the sunward side and the non-sunward side would be extreme. But what I forgot about is that for Venus, at least, really the dominating factor is the greenhouse effect. Mercury Mercury has the highest difference in temperature between the sunward side and the nighttime side. Venus, on the other hand, is about 400 degrees Celsius day in, day out. Doesn't matter what side of the planet you are. The atmosphere is so good at trapping heat that it effectively radiates or transfers that heat all over the world. So day, night, it's going to be 400 degrees Celsius. It would be really boring to be a weather person on Venus. And so again, if you're not rapidly rotating, the atmosphere is far less complicated, and so you're going to have far less weather and therefore far less erosionary effects. You're also incidentally going to have much weaker magnetic field. Whereas if the planet is more rapidly rotating like the Earth, the atmosphere becomes much more complex, and you have, again, more winds, more weather, stronger magnetic field, larger erosion. Howdy, Norm. And I think that is it for me today. So I know I was kind of bumbling around with this one, so I beg your pardon on that. Next time, which will be tomorrow, if all things go well, I will be talking about planetary atmospheres. I will talk about specifically, I will be talking about the terrestrial world planetary atmospheres, and I'll get into lovely things like Hadley cells and differential winds and tropospheres and thermospheres and all that kind of good stuff. And why is it that, technically speaking, our atmosphere is hottest at the boundary layer, if you want to call it that, between the Earth and space. And if I remember, I will also talk about why it has been claimed that the Earth's atmosphere actually incorporates the moon. Basically, the answer to that question, spoiler alert, is that we don't have a real good definition as to when the atmosphere ends. But anyway, oh yes, and I will talk about the infamous atmosphere gradient and what causes it, gravity, and talk about that, the pressure differential and the temperature differential, and so forth and so on. So I hope you've all found this educational and entertaining. As always, if you like this content, please like, share, and subscribe. I promise, tomorrow I will be going live and talking about the JWST observations, because it has been bugging me that a number of people have been coming to me and asking me, hey, did JWST debunk the Big Bang? No, it did not. And I will talk about it. I will tell you why it is these observations, if true, are, I wasn't going to say troubling, but intriguing would be much more the apt term, because very much like exoplanets didn't debunk the Nice model, it certainly is going to have us reevaluate how we believe early galaxies do in fact form if these observations hold out. Big if. If you'd like to help me out and the university out with our public outreach, please consider becoming a patron, or hit me up on PayPal. All of those proceeds go to paying our tour guides, basically our starving students, so they don't have to take out so many loans, and buying hand paddles and all that sort of other lovely equipment. Yes, clickbait is out of control. Like I said, I had a rant where I talked about how science communication needs to do better. And also, hopefully today, maybe tomorrow, I don't know. I also do plan on going live in my office, where I will talk about, speaking of science communication, this notion that if you're falling, we're not accelerating, the Earth is, and the Earth is accelerating up, and yada yada. And why that is, while I suppose technically true, a really, really horrible way to explain that to someone who doesn't have, shall we say, either an intuitive grasp or a more informed grasp of what it is that's going on when things fall in a gravity field, or things move through a gravity field. So anyway, with that being said, I wish you all a good one, and I will see you on the next one. Clear skies, and peace out.